Well, hello, welcome back. We're in chapter 2 now. And man, after that first one, I talked for an hour and 40 minutes. I didn't realize I was going to talk that long. I'll try not to talk too long this time. You poor students have to listen to me talk. All right, so chapter 2 is all about atoms and elements. So, chapter 1, we talked a bit about what chemistry is, what science is, and I talked about mixtures and got down to elements. And I said, well, an atom is the ultimate particle of an element. So, we're going to talk about that today. And so, right now, we pretty much more or less proven. We know that atoms are there because I see here in front of me, I got some pictures here. There's some figure 2.1 there has got some cobalt atoms, and then I've got NIST. Someone wrote NIST in atoms, and what's we can see them. What's the big deal? Well, Dalton and other people had some really hard time. Actually, the first idea of what atoms are the Greeks. They came up with the idea of atoms, but of course there were only four elements back then: earth, wind, fire, water, and they did not account for everything. Of course, we have more than four elements. We have 118, but we have a bit more. And but the idea of an atom still holds. And atoms, the Greeks' idea of atoms were a bit like Dalton's. They thought atoms were like small, indestructible spheres. So that's what Dalton thought it was. Okay, but let's talk about these images. So here is a cobalt image there, and then you've got the atoms here that say NIST, and if you look at them, they look kind of like pimples. So why do they have that shape? Well, they use something called a STM, a scanning tunneling microscope. That's STM, scanning tunneling microscope. And the way it works, you have a piece of tungsten. I should probably pick a different color. So you have a piece of tungsten, and it's like a bunch of grapes, and usually you go down, and then you have your surface, and let me just draw the atoms on the surface. And then what this what this thing does is it scans back and forth. So you have this piece of tungsten, and it's scanning back and forth. And when there's an atom here, so here's an atom, and here's the tip. The tip is moving in this direction. I'm just trying to draw a line. And what happens is as it moves a tip, you get a signal. So this atom here is giving a signal up to these atoms, and as the tip approaches it, it will start to give a signal. So rather than the atom being a sphere like this, the image kind of looks like that. It looks kind of like a rounded pimple rather than a sphere. And that's what you're seeing here. You're seeing the kind of rounded kind of surface. And that's just an artifact from the scanning tunneling microscope. So if you're wondering why it looks that way. But let me jump into Dalton's atomic theory. So Dalton took a few things. First of all is the law of conservation of mass. That is, in a chemical reaction or physical process, matter is not created or destroyed. The law of definite proportions, that for a specific compound, the elements are put in set proportions for that. And then the law of multiple proportions, if you have two or more elements that form different compounds, each of those compounds have set ratios, but they're different from each other. Okay, so those are the three laws that he took, and he took it a little bit further to say that these are atoms, that there's these tiny things called atoms that exist. They're small, they're all the same for each element, they're indestructible, and what you're doing in chemical processes, you're just changing atoms. And he was right about something. He was right about atoms. He was wrong about them being indestructible. He was wrong about them all being the same. We'll learn later something called isotopes, where you have the same element. Each element has the same number of protons, but a different number of neutrons. Those are known as isotopes. And uh, so he was a little bit wrong about that, and we'll talk about that later as atomic theory has developed. So this is here illustrates the law of definite proportions and the law of conservation of mass. So you have here, you have a set amount of sodium and a set amount of chlorine reacting to form a set amount of sodium chloride. So the amount of mass is conserved in this process. And also you have the set ratio to form this compound. This one here shows the law of multiple proportions, that if you have oxygen with 1 gram of carbon, if it's 2.67 grams, 1 gram of carbon, that's to form carbon dioxide. If it's 1.33 grams to 1 gram of carbon, that's carbon monoxide. So this is carbon and oxygen, two elements, but two different ratios to form multiple different compounds. Each compound is different, but each one is set in a set ratios. That's the law of multiple proportions. And we've already, I mean, atomic theory is so heavily proven that I'm not going to show you without the atoms involved. And you see the atoms here are involved in all the pictures. Okay, so here's Dalton's atomic theory. I mentioned that you have atoms, same mass. Yeah, each atom is the same. The other elements are different. Atoms combine simple whole ratio numbers, and atoms one element cannot change into elements of other element. That's mostly true. So that is mostly true. Okay, so, and I'm going to spare you some of the history. A lot of it's fun. So law of conservation of mass, that was done by a French aristocrat called Lavoisier. And he and his wife, among other things, they went around. He was a bit of a nut. And something to notice about science used to be both religious and aristocracy. So the French, they love to do mathematics and hold competitions and that kind of stuff. But Lavoisier, he was a nobleman, and he, for instance, tried to just survive off of milk rather than a balanced diet to see if he could do it, and capture the attention of his wife. And they just did a bunch of different processes and did chemical reactions. That's what they did for fun, is they sat around and did a bunch of chemical reactions. Sounds like a good time to me, of course, but I mean, it is rather unique. But they fell in love and developed the law of conservation of mass. You know, match made in heaven. Also, there's more history here. I didn't cover the Millikan oil experiment and cathode rays. They're just breaking the atom apart. So we broke the atom apart. We found out that electrons, you can rip electrons off an atom. And from that, we came up with the plum pudding model. Plum pudding model, this would probably be better described as like the blueberry muffin model in contemporary American society. Like a blueberry muffin, you know, it's a lot of muffin with little tiny blueberries in it. That's the same idea with a plum pudding model. So you have this big sphere of positive charge, and you have electrons floating around in that big sphere of positive charge. So then Rutherford came along, and he said, "All right, well let's look at this plum pudding model a little bit more." And he was kind of, you know, because Dalton said, "Hey, atoms are solid, they're indestructible," and then with Millikan and other experiments, we have the plum pudding model. And so he's like, "All right, we're gonna verify the plum pudding model is correct, because if the plum pudding model is correct, so what he did, I mean, I guess it's an experiment. He took an alpha source, so took some radiation and encoded it in lead and put a hole in it, so some alpha particles were flying through. And gold, you can hammer gold really, really thin. So he took some gold, and then he put some a phosphorus screen around it. And if radiation has a phosphorus screen, it flashes. Okay, so, and he's like, okay, well, if Dalton is right, then no radiation will go through. If Dalton's wrong and plum pudding is right, we're going to have all the alpha particles just go right through to verify the plum pudding model. And of course, he found out that neither were correct. But so what Rutherford ended up doing is he's a professor, and what he did is he had his grad student do this. One of his grad students. No one knows the grad student's name. Well, maybe I'm sure someone does. I don't know the grad student's name, I should say. But I mean, this is in the 19th century, so we don't have computers. He gave the grad student a clicker, kind of like, you know, when you're going to Costco or a club and people click to see how many people come in. Gave a grad student a clicker and basically said, all right, I want you to sit here and click every time you see a flash of light, and then after some time, move over, and I want you to collect all the data from around this and give me the data. And so this grad student, he sits there in the dark, But it has to be in the dark. So like for 2 weeks, he did this, and then gathered the data, presented it to Rutherford, and Rutherford goes like, "This can't be right. This is, what he found. Well, says this can't be right. Do it again." So the grad student did again, and grad student got the same result and presented to Rutherford, and I was like, "You still did it wrong." The grad student's like, "Hey, look, man, you've been doing professorly things like smoking your pipe and going to drinking coffee with your colleagues. I've been here in the dark, and I've been collecting the data. This is right. You can go and you can try this yourself." So Rutherford went like, maybe this data is right. And this is what the data was. So, I mean, like I said, we were looking at Dalton, looking at the plum pudding model, everything would go through Dalton's model. None of it would go through. What he found out was most of them went through and some of them were deflected. And from that, Rutherford came up with the idea of the nuclear atom, that the atom is mostly empty space, and the nucleus that's where most of the matter of the atom was in this nucleus. And an atom, just to clarify, an atom is not full of empty space. The electron cloud occupies the most of the volume of the atom, but so it's not empty space, but it's just not very massive compared to the nucleus. And so Rutherford came up with the idea of a nuclear atom. And this is what an atom is made of. So atoms are made of protons, neutrons, and electrons. And the protons and neutrons are found primarily in the nucleus of the atom. They're not very frequently found outside. Their wave function doesn't really exist outside of the nucleus unless they leave the nucleus for whatever reason, or like the atom splits apart, for instance. But electrons are found predominantly not in the nucleus. The electron does spend some time in the nucleus, not very much, but it's mostly outside of the nucleus. And protons and neutrons there. Protons and neutrons, we give it the mass AMU. That's the atomic mass unit, and it's based off of carbon-12. We say carbon-12 nucleus has 12 AMU. So that's what we base the mole off as well. And the charge, we just give proton +1, electron -1, and that's a plus 1.6 times 10 to the minus 19 coulombs. Coulomb is the unit of charge for the metric system. So, and you can see a neutron is ever so slightly more massive than a proton, because a neutron can decay into a proton and do an electron. That's known as a beta decay, and a free neutron will decay by itself as well. So neutrons are slightly more massive than protons, but they're about the same mass. They're roughly about 2,000 times as massive as an electron. So in a nucleus, you're looking at on the order of 2,000 or more, because there's most elements have more neutrons than one in the nucleus. So you're looking on the order of 2,000 times as much mass in the center of the atom versus the electron cloud. So that's why in a helium nucleus, that has a mass of 4 AMU. That's why helium, an alpha particle, just can fly right through it, because it's just not a lot of matter there to stop it. Okay, and elements. So talk about Rutherford proved the nucleus. We have elements then that have nuclei, and the elements, they're defined by the number of protons in the nucleus. And when you see what I mean by that, so this isn't used as frequently. It's only used for nuclear chemistry or designating a specific isotope. But you have a chemical symbol, and I'm just labeling X here. It's usually something like Cr for chromium. The bottom number in it on the subscript, this is the atomic number. This is the number of protons, and it's actually redundant with the chemical symbol. And then the mass number in the top, this is the number of the protons plus the number of neutrons. So the mass of a proton, mass of a neutron is going to change depending on the environment. So the lightest protons and neutrons are found in the iron 28 nucleus. So, or 20, whatever, 58, sorry. So, I'm sorry, iron 56. 28 is the atomic number times 2. That's the most stable nucleus, but um, they lose uh, mass by equals mc squared, and they're formed in stars. At least most of them. Some of them we can form in other ways, but most of them are formed in stars. So, but we can cover that later and talk about nuclear chemistry. Okay, but let's talk about this. Elements are defined by the number of protons. And so if you look at the periodic table here, and you will learn much and much about the periodic table. Let's look at gold, for instance, right there. Element number 79. That means it has 79 protons in the nucleus. Mercury right next to it has 80 protons in this nucleus. So, okay, and mass number, atomic number. Well, let's talk about isotopes. I guess let's talk about isotopes first. So we have this way of doing it, what I've written in my electronic ink. Sometimes you see things like neon 20. That means 20 neutrons. So if you see here neon 20, and this symbol here, you see where it's 20 and 10. That's supposed to denote what's up here. So isotopes. What an isotope means, same number of protons, different number of neutrons. And so neon 20, there's neon 20, neon 21, neon 22. And this is the relative abundance, and this is the terrestrial. So this is here on Earth. So the relative abundance is there. And actually, if you've read the textbook, you'll see that different places actually have different abundances. So it's not exactly something. It depends on where you're at and your source of things. For instance, I mean, so the classic example is carbon in plants has a little bit more, in living creatures has more carbon-14 versus if you look at carbon in rocks, for instance, essentially has no carbon-14. So it depends on the source of the carbon. There can be a different abundance of isotopes. But seen here, we have neon with 3 primary isotopes, and the abundance of that listed here, roughly 90% neon 20 and 10% neon 22. It's no accident. The nuclei are much more stable when there's an even number of protons and neutrons. So you're not gonna there's only a very few elements that have odd protons and neutrons that are stable. But okay, so let's talk about mass number, atomic number. Argon isotope has a mass number of 40. How many neutrons does it contain? So you look at argon, and argon, let me move this up a little bit more. Argon is right here, has 18 protons. So this means that you have argon, and this is going to be 40 and 18, like so. So the 18 is the number of protons, the 40 is the mass number of protons plus the number of neutrons, and just get the number and try to take the top minus the bottom. The answer is 22. Okay, so what about ions? Ions are atoms. So an atom is neutrally charged. So an atom is neutrally charged. Ions are from atoms gaining or losing electrons. A positive ion, also known as a cation, is from the loss of electrons. So ripping off electrons will cause the atom to become a positive cation. And if you have a hard time remembering that, think of the T. I can't see that. I'll pick a different color. Think of the T as a plus sign. You still can't see that. Think of this T as a plus sign. The T in cation is the plus side. So loss of electrons. So atoms have electrons move around. If the protons move around, the element changes. So protons moving around is very difficult. Can protons move around? Yes, they can. It is very difficult to do, though, because protons have a huge amount of energy that they have to be put in to move from the nucleus, whereas electrons, much less. So electrons own the flow. And besides, if the protons leave the nucleus, or if protons are enter the nucleus, the element will change. It'll change the element. And if an atom gains electrons, it becomes an anion. So if you want to remember this way, an anode is the source of negative charge in a battery. So cathode is the source of positive charge. Anode is the source of negative charge. So most people think of cation. It's cation, not cation. Cat, like the four-legged fuzzy quadruped, cation. So, okay. Now let's talk about the ions. How many electrons are present in the oxygen -2 anion? So we have to go back to oxygen on the periodic table. Here is oxygen. Oxygen has 8 protons. So just to emphasize this, oxygen here has 8 protons. And 8 protons means it normally has 8 electrons for it to be neutral. For a -2 ion, it needs 10 electrons. So this one here needs 10 electrons. And that's because oxygen has 8 protons, and it needs an extra 2 electrons to give it the -2 charge. Okay, so we are going to go much more in depth into the periodic table. And of course, I'm sure you feel this way as you're listening to me in this class, like, my gosh, we have to know everything right away. Not necessarily. I mean, we're going to build up to it, but there's some things you should know, and these are in the periodic table. It's built this way. It'll make more sense when we talk about the quantum mechanical model, and this is built off of quantum mechanics, but there are elements here that have predictable charges. So this is one of the reasons why we have the periodic table the way it is. And you have the first column denoted 1A, although hydrogen is not normally included in this, but those are known as the alkali metals, and those all have a +1 charge. And then group 2A, those are known as the alkaline earth metals. Next to lithium, that blank spot, beryllium should be there. Beryllium behaves just like the others. Beryllium's just extremely toxic. So I guess that's the reason why I didn't put it there. But it does form a +2 ion, even though it's not listed. But it's just, like I said, so toxic we try to, like, someone offers you beryllium, don't take it, kind of thing. It's just really, really toxic. Not the most toxic. Like, polonium is far more toxic, but still, it's not something you should keep lying around. Oh, you can see hydrogen in 2 places. So hydrogen is also in this group 7A, where they tend to form -1 charges. And there's 8A, the noble gases. So this is British English, so noble means unexcitable. It used to be called the inert gases, but then we got them to react. Now they're just the noble. They tend not to react. It's like the nobility in England. It's like, oh my, this is the worst day of my life. Oh, it is now the best day of my life. I am so noble. You cannot see my emotions because I am so stoic. That's the idea behind noble gases. They're the stoic gases. They don't show their emotions at all. They don't show their reactivity. And the halogens, group 7A, halogen is Greek for salt forming. They are very reactive. They form -1 ions. Then you have oxygen, 6A, oxygen family. They all form -2 ions, and nitrogen and phosphorus form -3, and aluminum forms +3. And we will learn this later, but this has to do with they want to the electron configurations that are similar to noble gases are very stable, and that's the reason why they bond that way. We'll cover that more when we come to bonding, but there are predictable charges there. Okay, so we're talking about elements. The elements of life. So this is what we are by humans. So by mass, we are very heavily hydrogen, or we're very heavily oxygen. So by mass, we're mostly oxygen. You look at atoms, atom percent, we have a lot of hydrogen and we have a lot of oxygen. Why is this not surprising? Because we have a lot of water. So much of the mass of our body is from good old H2O water, so it's not surprising that you see that. And we're known as carbon-based life forms, but you can see that we're only about 20% carbon by mass and 10% by atom. Carbon is a very interesting element. It's extremely unique. It's a non-metal. Oh, we haven't talked about metals and non-metals yet. But it can conduct electricity, but it doesn't always conduct electricity. But the most unique thing about, in my opinion, is carbon forms straight chains. That's very unique. You don't see that in any other elements, and that's where we get our structure. So some people say, oh, you can have silicon-based life forms. I've worked with silicon. I did some research with clusters, and silicon at about 0 to, well, I guess one to about 19 atoms forms this kind of football-shaped prolate clusters, and after 19 atoms, they form kind of spherical, known as cage-like structures. If you put carbon in a vacuum chamber, let it react, it tends to form straight chains, and that's the reason why we have certain structures in our bodies, things like cell membranes and DNA and these types of structures that really rely on straight chains. You would not be able to have a DNA molecule or a cell membrane phospholipid bilayer molecule that was an analog of silicon. It just wouldn't happen that way. And also, silicon would be more reactive to certain types of things. So proteins would not be as stable if they were made from silicon rather than carbon, for instance. So yeah, there's not going to be any silicon-based life forms, at least not life that has like the similar types of structures in our cells that we have. Anyways, okay, I'm digressing. Okay, so you can see that we have quite a bit of oxygen, carbon, hydrogen, nitrogen, and we've also given this the name CHON. Carbon, hydrogen, oxygen, nitrogen. So we look for this when we're looking for life in space. So one of the things we look for is life outside of the Earth, and we're looking for these four elements because they're found in life, and things like proteins, for instance, in the nitrogen. And we can see we have a bit of calcium and phosphorus as well. That's from our bones and teeth, and other things like iron, a little bit of copper, magnesium, that kind of stuff. A little bit of sulfur as well. We have that in our cysteine proteins, iodine, our thyroid, these kind of things. So, but that's what we're made of. But of course, the story we're made is more than just what we are. Our atoms are made of. Okay, I didn't include this in this lecture, but the book talked about mass spectrometers. What you have to know is that when you throw things in a mass spectrometer, it separates them in charge to mass ratios. So a danger with that is if you have an atom with mass 40 with a +1 charge, that's going to show the same signal as an atom or as a molecule or atom that's 80 AMU with a +2 ion. But they tend not to form multiple ions. +1 tends to be by far the most common. But when you take elements and you throw them into a mass spectrometer, they tend to separate out, and you can see them. You can see by their isotopic ratios. So you can see here on the left, you have chlorine. Chlorine has 35-37 with about a 3 times as much, about a 3-to-1 ratio, 3 times as much chlorine 35 as chlorine 37. And silver is about an even split. Bromine is also another one that has an even split like this. So we have different ratios of elements, and this is terrestrial, so meaning on Earth. So if you ever wonder, like sometimes say, oh, this rock is from Mars, like, how the heck did they figure out it was from Mars? It's they look at different ratios. They have it's not of this Earth because the isotopic ratios are different, and they've also looked at samples from the moon. So some people don't think that we've gone to the moon, but besides the fact that we have mirrors on the moon that humans put there, that we check the distance, we've got some moon rocks back, and they're different than Earth rocks. And one of the ways that they're different is that the isotopic ratios are different on them. Oh, one thing I should note that the elements are all the same for every star, planet in the cosmos. If you go to Mars, there's not new elements. If you go to Proxima Centauri or Alpha Centauri, it depends on the time, the closest star other than the sun to us, the matter there is the same. If we go to the Magellanic Cloud, it's a galaxy that orbits our galaxy. They There's going to be the same elements there. So the elements are all going to be the same throughout the entire cosmos. The isotopic ratios can be different though. And if you look at the periodic table, though, we have the mass, the atomic mass. Do we have that on this? No, I guess. Oh, we don't have that there. There's the bottom number on the periodic table. It's the atomic mass. It's different than the atomic number, and the atomic mass is the weighted ratio of the isotopes here on Earth. And this is to show you how that calculation takes place. So copper has two naturally occurring isotopes, copper 63 with that mass and that abundance, and copper 65 with that mass and that abundance. What is the atomic mass of copper? And so let's do this, and it's the weighted mass, so it's the ratio. So what you do is the atomic mass. This is going to be equal to the mass of 1, so it's going to be 62.9291 times the fraction. So 69% is the fraction 0.6917 plus 64.9278 times the fraction 0.3083. And you throw this in your handy dandy calculator, and what do you get? Then you get 63.55, 63.55. You actually get 63.5456, but then rounding to the 4 sig figs, you get 63.55. And so this is the weighted average of the different isotopes of copper found here on Earth. And if you're wondering why the 62.99 or 62.9291, the reason for that is, so you look at a proton and a neutron, as it populates the energy levels in the nucleus, it loses energy. So a free proton, a free neutron is going to have more mass. It's going to be more massive. As it forms an atom, it becomes less massive and it releases energy. And that is the idea behind energy behind nuclear fusion. Copper is actually going to be as stable as iron. So iron is the most stable nucleus. But we can talk about that more if you take me in chemistry 162 and we talk about nuclear chemistry. Okay, so and next thing I want to talk about is the mole concept. So one thing about atoms, they are very, very tiny, and but you can count them. You can count them by mass. Maybe I'm showing my age. I remember back when I was in my 20s, I'm 40 now, going to Vegas. When you played the slot machines, they gave you a bucket, and then the quarters, you would win quarters when you did the slot machines. And then when you're done playing, you took the bucket to the front desk, and then they would weigh the bucket. You could take the quarters and run, of course, but you know what the heck are you gonna do with all those quarters? And you could take it to the cash out, and they'd weigh the bucket, and then they give you money. Basically, I mean, you're trading quarters for bills, but they're not going to count them one by one. They just weigh it, right? So the same thing is we can count atoms by mass, and we use a mole. We use a mole for this, and it's sometimes referred to as a chemist's dozen. So dozen is 12. 12 is a very cumbersome number, right? So the idea is like when you buy eggs, you don't say, I'm going to go buy 12 eggs. I'm usually say I'm going to get a dozen. We even use terms like when I go to Costco, I usually get 18 eggs. That's a dozen and a half. You know, I even think of it now. It's like 1.5 dozen of eggs. And so, or 6 eggs is a half a dozen, right? So you can take something like a dozen, and you can apply a fraction to it. So we do the same thing with atoms, and we use this huge number as Avogadro's number, and Avogadro's number is 6.02214 times 10 to the 23rd. So that's a 6 with 23 zeros after it. That's a big number. That's a really big number. It's based off of Avogadro's number is based off of 12 grams of carbon 12 is 1 mole. So we base it off of that. And I mentioned this last lecture. We might change this. Probably not in the too near future, but we'll see. Who knows? Who knows when if and when they'll change the definition of a mole. Okay, so calculate the number of carbon atoms in 2.45 moles of carbon, and this is when you use a dimensional analysis. So 2.45 moles of copper. So Cu is copper. And then we have 6.02 times 10 to the 23rd copper atoms over mole of copper. And the units for Avogadro's number, it just means number. It's just particulates. So whatever it is you're looking at, so if it's a mole of carbon, it's going to be the carbon atoms. So, and you plug that in your calculator, and you get 1.48 times 10 to the 24 copper atoms. That's a lot of copper atoms, right? So it tells you atoms are very, very tiny. They're very, very tiny. And just like how we use a dozen and you can use fractions when it comes to dozen, we're using fractions when it comes to atoms as well. So the moles. Well, actually, I'm sorry, you can't use fraction with atoms, they're whole numbers, but the mole, you can use the mole and have a fractional value of the mole as well. Okay, so let's do some more problems like this. So you get, and the point of this is you can watch me do it, and you get used to setting up these problems and calculating them and using dimensional analysis for them. Dimensional analysis, at least right now. So you do a lot of you'll use it for most of this class, actually. Okay, calculate the amount of carbon in 0.0265 grams of pencil lead. So, and the pencil lead is made of carbon. So the idea here is 0.0265 grams of copper, and you have to look to the periodic table. So I'm sorry, it's not copper, it's carbon. I'm still, the last problem stuck in my head. Moles of carbon, and this is 12.01, I think, when you look at a periodic table. Let's see here, 12. Yeah, at least that's what the book is doing. I think I made this line too big. We can stop there. So it's 0.01 grams of copper, or carbon. Okay, so, and you can see, I didn't do it the last problem. You can see that the grams copper cancels. So then we do this, and we're left with 2.21 times 10 to the minus 3 moles of carbon. So this way you can go from mass to moles to numbers. If you wanted to go on to numbers, you would multiply by 6.02 times 10 to the 23rd. That would tell you how many atoms of carbon you have there. Okay. And last problem, the mole concept. I was just thinking, we did a sphere in the last class. We're not going to be doing all these spheres. This is just, I guess this is just to train you in terms of problem solving, and this is just an easy one that you have an equation. So don't worry, we're not going to sit around and measure spheres and calculate spheres. This is just kind of your warm up for the semester. But anyways, aluminum sphere contains 8.55 times 10 to the 22nd aluminum atoms. What's the sphere's radius in centimeters? The density of aluminum is 2.70 grams per cubic centimeters. So you're given the number of atoms and the density, and then you need to find the radius. So the radius, The volume of a sphere is 4/3 pi r cubed. So we've done this before, right? So 3v over 4 pi to the cube root is the radius. So now our next thing, we know how to solve for the radius. Now we need the volume. So the volume then, so where are we in the volume? Well, we have the number of atoms here, and we're given the density. So from the atoms, we can figure out the moles. From the moles, we can figure out the mass. From the mass, we can get the volume. So, and then we plug it in. So let's do this then. So 8.55 times 10 to the 22nd aluminum atoms. And we have mole of aluminum to 6.02 times 10 to the 23rd atoms aluminum. And aluminum is 27. Let's see what the book says for it. Okay, 26.98. I would have just do 27, but what the heck? I'll stick with the book. 26.98 grams aluminum per mole aluminum. So now we have mass aluminum, and then we need the volume. Volume is then 2.70 grams per cubic centimeters. You see, I'm dividing by it there because to have the units work out, right? Because I need a volume. So now that I calculate, once I calculate this term, you can then put it in there to the volume. It'll give you the radius. So if you calculate this out, you put it out, this is going to be 1.4187 centimeters cubed. And then you plug this, like I said, into that equation, and what you end up getting, radius, is going to be 0.697 centimeters. Right, so then you have the answer there. Again, like I said, we're not going to be sitting around calculating the size of spheres all semester long. This is just the beginning, and we're just trying to get you used to doing calculations and that kind of thing. So don't worry, you're not going to be doing this all that much. But okay, so we've gone through and talked a little about the mole concept. I know it's been very, very brief, but I'm also assuming some of you had some chemistry before. I've tried not to drone on and on like I did last time. Hopefully this has been a more enjoyable lecture for you than last. So I will see you then. Oh, 43 minutes. See you next chapter.